In this video, we will be presenting our CVPR' 2022 paper, LGT-Net. Indoor Panoramic Room Layout Estimation with Geometry-Aware Transformer Network. The goal of room layout estimation task is to estimate the 3D room layout from a single RGB panoramic image. The room layout can be represented as a horizontal 2D shape formed by floor boundary and vertical room height. However, previous approaches indirectly predict these two parts. They cannot get the geometric awareness in horizontal and vertical directions simultaneously. Inspired by LGT-Net, we use horizontal depth to represent floor boundary. The camera height is known. But during training, we set a scale so that the camera height to 1 and then get the horizon depth under this scale. So the combination of a horizon depth sequence and room height can represent the 3D room layout. Furthermore, suppose the room layout follows the Atlanta or Manhattan world assumption. In that case, the model needs to be constrained to get a more regular 2D shape that reflects the flat walls, instead of just relying on post-processing. There is the overall architecture of our proposed network. The feature extractor, like LGT-Net, is based on ResNet 50 to obtain a feature sequence. Then SWG transformer further processes the feature sequence. Finally, two branches output a horizontal depth sequence and room height value. It is worth noting that we can calculate the normal and gradient by horizon depth. They are used to calculate the planar geometry awareness loss. Here are the various blocks in SWG transformer. And the difference between them is the operation before and after MSA. The window blocks are used to reduce computation and enhance local modeling ability. However, each token corresponds to a horizon depth value. So the global block is necessary to enhance the global awareness of each token. In the figure, WRPE and GRPE represent relative position embedding in window block and global block. In window blocks, the relative position encoding is similar to SWIN transformer and is denoted as WRPE. But to correspond to the circular structure of the global panoramic sequence, we propose a relative position encoding with asymmetric representation in the global block. We calculate the L1 error of horizontal depth sequence and room height to obtain omnidirectional geometry awareness. To supervise the planar attributive walls and turning of corners, we calculate the cosine similarity of normal and L1 error of gradient to enhance planar geometry awareness. Therefore, we use the total loss function here to enhance both aspects. Qualitative results on Matterport layout dataset are shown here. The first column shows that LGT-Net and LGT-Net predict discontinuous layouts at the left and right borders of the panorama. However, our proposed SWG transformer treats tokens equally at all positions. The second and third columns show that our approach better estimates the boundaries far from the camera center and those of complex room layouts. Meanwhile, the visualizations of floor plans, normals and gradients show that our approach offers better results by planar geometry awareness. Here are the qualitative results on XIN dataset. The first column shows that our SWG transformer can better process the left and right borders of the panoramas. The second column shows that our proposed approach has an advantage on non-flat ceilings layouts since it is not affected by the ceiling boundary. The third column shows that our approach performs better with furniture occlusion than other approaches. Qualitative results on Matterport layout and XIN datasets show that the performance of our proposed approach is better than all other approaches. Moreover, similar to the idea of VIT, we split the panorama into patches by patch embedding and feeding them into our proposed SWG transformer. The results show that such VIT architecture achieves comparable performance on the large XIN dataset. Although our proposed method is not optimized for cuboid room layout, it is close to SOTA. Ablation experiments verify the effectiveness of each component proposed in our paper, including geometry awareness loss function, network architecture, and position encoding. The most significant improvement comes from the omnidirectional geometry awareness of the layout represented as horizon depth and room height. It is worth noting that pure VIT architecture does not achieve comparable performance in Matterport layout dataset. We argue that VIT architecture relies on large datasets like XIN to perform better. Nevertheless, we believe that better VIT architectures will be applied to panoramic tasks in the future. If you are interested in our work, visit our online demo or GitHub page. Thanks for watching.